Okay, good afternoon, everyone. So today the first speaker is from East China Normal University, Professor Zhang or Tong Zhang. He will talk about Richter severity inequality for irregular three-fourths of genotype. Please, yeah.
Okay, so I don't know if my internet is stable or not. So in case, I mean, to keep safe, maybe I will maybe stop my video part and I only share my screen. So in order to save the band, okay. So sorry about this. So I stop this part. Okay, good. So yeah, so thank you very much for the invitation and thank you very much for the introduction. So it's my great pleasure to give a talk here. In fact, I mean, not every week, but every 2 weeks, maybe. Usually, if I miss some of the talk of this seminar, I will follow the video. So somehow I'm a follower of this seminar, and I think I learned a lot from this seminar series. So it's my great pleasure to contribute a bit of my research, and I also want to apologize a bit because I think some of the audience may have heard this talk before. So I will try my best to talk about something new or something of some of my new understanding towards this topic. Okay, so today I want to talk about this Noether severity inequality and this inequality for irregular three-folds of genotype. And this is a joint work with Hu Yong, Yong Hu, and who is now a faculty member at Shanghai Jiao Tong University. So I will first start from the motivation, and if anyone has questions, just feel free to interrupt me. So I think the motivation comes from the classification problem of algebraic varieties. So this is the motivation, and somehow we want to classify or describe as many varieties as possible. And of course, there are lots of different methods towards this classification. And today I want to focus on the viewpoint of the geography of algebraic varieties. And so what is the geography of algebraic varieties? In fact, I have checked many books and there's no formal definition, but I looked up some research paper. For example, I read a very classical paper written by Pearson, and he had a description. So somehow I roughly follow his description. So there are 2 steps in order to classify algebraic varieties using the geography approach. And the first step is somehow to find some numerical relations. And these relations are among the birational invariants of varieties. And this is mainly about varieties of genotype. So I hope that you can see my writing. Okay, good. So is that okay? Yeah, okay.
We can see you, yeah, we can see you.
Okay, good. Okay, good, thank you. And this is the first step. And the second step is to somehow use this relation to classify or describe some varieties that you may be interested in. So So I write this explicitly classify or describe varieties. And the method is using this numerical relations. Okay, so in the next page, I want to explain what are the birational invariants that we are interested in. So here, so I consider a variety X. This is the variety X. And I assume this variety X is a smooth projective variety of genotype. And we usually consider this problem over the complex numbers. So I wrote over C. Okay, and in the following, I write like 4 classical birational invariants that we are interested in. The first one is the canonical volume. So, or I think in some research paper, they call it volume. And here I write canonical volume. And what is the canonical volume? And this is defined as a limit sup. This is a limit sup of a ratio. And the numerator is the dimension of the it's just the mth plurigenus of the variety. So this is h naught of m times kx. And the denominator is somehow m to the power of the dimension d and over the d factorial. So here d is a dimension. So d is a dimension. Okay, so this is the first invariant that we want to consider. Moreover, if you assume that this variety is of genotype, then automatically this volume is positive. So it's bigger than 0. So it's a meaningful quantity. And the second one is the geometric genus. This is defined as usual. So it's just the global section of the canonical divisor or the dimension of the canonical linear system. This is always non-negative, but in some case, this could be 0. And even if it's of genotype. So, and the third one is called irregularity. This is just the first cohomology of the structure sheaf. And this is H1 of OX. And since we are consider the varieties defined over complex numbers, if it's smooth and projective, and we can use the Hodge symmetry to get that this QX is just the global section of the holomorphic one form. Okay, and the fourth one is the Euler characteristic. And here, so I wrote like 2 versions. The first characteristic is about the structure sheaf, and the second one is about the dualizing sheaf. And as we all know, if the dimension is even, then those 2 numbers are the same. Otherwise, maybe they differ by a minus sign. So the relation is roughly like chi of OX is -1 to the power of d times chi omega x. Okay, and here I only listed like 4 of the invariants. In fact, there are more. And for example, you can consider the plurigenera, and those are also very interesting birational invariants. And many algebraic geometers, they have considered how to estimate those numbers. And in this talk, I mainly focused on those 4 invariants. Okay, so any questions so far? Okay, good. Okay, then I will continue. So I think it's better to give some example about the geography of surfaces of genotype. And this is somehow is the origin of this development of the geography of geography classification of algebraic varieties. So here I assume that I have a surface S. This is S, and assume it's a smooth projective surface of genotype, and it is defined over complex numbers. And there are many interesting numerical relations among those birational invariants. So here I gave two fundamental ones, and those two are very classical, and you can find them in some like research monograph of the algebraic surfaces. And the first one is the Noether inequality. So this part. So I use, okay, it's this one. This inequality says that you can give a lower bound of the volume and in terms of the genus. So it reads as like a volume is at least twice of the geometric genus minus 4. And this inequality is sharp. So it's somehow it's sharp or optimal. And this is a lower bound of the canonical volume of a surface of general type. And there is also an upper bound, which is called the Miyaoka-Yau inequality. And it says that the canonical volume of the surface of general type is bounded from above by 9 times the Euler characteristic. And this inequality is also sharp, it's optimal. Okay, and I also given further inequality, is this one. And this one just follows from the definition of the Euler characteristic, because in this time, under this situation, so the chi is just the same as PG minus Q and plus 1. So by the non-negativity of the QS, then you can obtain this one. It's quite easily. So it's there are like 3 inequalities. Okay, and this somehow shows what is the first step of the geography of algebraic varieties, and algebraic surfaces of general type. And the second step is to use this numerical relation to classify some extremal case that maybe some people are interested in. For example, there's a very classical work. It's a classify the surface satisfy the Noether equality. So this is a Noether equality. And usually people call such a surface a surface on the Noether line. And such a surface or such surfaces can be fully classified. And this is a very fundamental work of Horikawa, I think in the 1970s. And he somehow gave all the structure of such surfaces, and he even calculated the deformation type and also the fundamental group, the topological fundamental group. And those surfaces are all simply connected. So it's very interesting piece of work. And the other extremal case is this Miyaoka-Yau line. I write this. This is Miyaoka-Yau line. And by the classical work of Yau, and we know that such surfaces can be, so we know its universal cover of such surface on the Miyaoka-Yau line. And the universal cover is nothing but the 2-dimensional complex ball. So it's just like this. So I write B2 as the 2-dimensional complex ball. So from this page, you may see that, so if you consider the geography question, first, you need to find some interesting numerical relation, and then you can try to classify the extremal case. And if it's possible, then you can classify some sub-extremal case, or like, and you can keep working out. But I think it's not so easy to classify all the things. Okay, so this is something about geography of surfaces of genotype. I think most of the audience, maybe, I think some of you may know more than me. Okay, so that's this part. And now I want to slightly talk about the geography problem for higher dimensional varieties. So on this page, I just assume that I have a variety X. So this is a smooth projective variety of genotype, and I assume it's defined over complex numbers, and the dimension is D. Okay, then a natural question is how to find some higher dimensional version of the Noether inequality or the Miyaoka-Yau inequality. So the first result I want to mention is a previous result by Menchen and Zhang. And they show that in any dimension, there is a Noether inequality. So of this form, so it's, which means that there are two positive numbers, AD and BD, such that once you have a D-dimensional variety X of genotype, then it satisfies this kind of Noether inequality. So, but usually it's very hard. I mean, for me, it's not easy to find what are the best possible of the two numbers AD and BD. But recently there is a very interesting piece of work, and this work was done by Yongkai Chen, Meng Chen, and Chen Jiang, and those three authors. They find the explicit value of AD and BD when D is 3. So in this case, they prove somehow they find the three-dimensional version of the Noether inequality. And their result is as follows. So suppose you have a threefold X of genotype defined over complex numbers, and you can put some constraint on the geometric genus, and this constraint is very mild, I think. So if you assume that the geometric genus is at least 11 or at most 4, so, and suppose you have this assumption, then you have an optimal Noether inequality like this. So it reads as the canonical volume is at least 4/3 times the geometric genus minus 10/3. And this is sharp, so optimal. Of course, before their work, I think some of the people may believe this inequality holds, because if you assume this X is smooth and minimal, or Gorenstein and minimal, which means that the minimal model has very mild singularities, and this inequality has been proved, I think, by the work of Menchen, Deqi, Zhang, and Catanese, and later by the work of Yongkai Chen and Menchen. So before this work, there has been many contributions towards this inequality. Okay, and on this page, the final thing I want to remark is that there's no Miyaoka-Yau inequality of the previous type, which means that if you want to get something like this, if you want to bound the volume from the above by the Euler characteristic of the structure sheaf or the dualizing sheaf, it's somehow impossible. The reason is that you cannot control the sign of this Euler characteristic, even though you assume that the variety X is genotype. Sometimes this character could be positive, and sometimes this character is negative. So there's no uniform way to get a Miyaoka-Yau inequality of this form. But if you only care about, like, I think C1 and C2, there are some recent work. I forgot the name of the authors, but they somehow get a Chen number inequality between, I think, C1 and C2. So that's another form of the Miyaoka-Yau inequality, but not this form. Okay, so this is somehow an introduction of the geography of higher dimensional varieties. And any question about this? Okay, good. And in the following, I will slightly introduce, the irregular varieties. Okay, so in this talk, I'm most interested in the irregular varieties. So suppose I have a variety X, which is a smooth projective variety, like let's say defined over C. And when it can be called an irregular variety, and if its irregularity is positive, for example, if I think the definition is just as follows: if the irregularity Qx is positive, and then this variety X is called an irregular variety. I think there are many irregular varieties. For example, if you have a smooth projective curve of positive genus, then it's irregular. And abelian varieties are irregular. And so you can take the product of abelian varieties with other varieties. They are also irregular. So there are many irregular varieties, and it's form a very important class of all algebraic varieties. And so usually people study the irregular varieties using the Albanese map. So this is Albanese map. I think here I don't want to give the precise definition of the Albanese map, and I just want to say that this is a map from X to an abelian varieties to an abelian variety A with some universal property. And this abelian variety A is usually called the Albanese varieties of A. So our notation will be like ALB X. This is A. And from this Albanese map, we can define the so-called Albanese dimension of X. So this is a number. So the Albanese dimension of X is just the dimension of the image of X under this Albanese map. For example, if you have an abelian variety, then you know that the Albanese dimension of an abelian variety is just itself. So this is a typical example of varieties of maximal Albanese dimension. So we say that a smooth projective variety is of maximal Albanese dimension if its Albanese dimension is equal to its dimension. So it's if this holds. Okay, and this is something about irregular variety. So it's just a very brief introduction. And then I want to introduce something about the geography of irregular varieties. So I want to start from the surface case. So suppose I have an irregular surface of genotype. So here on this page, S will be an irregular surface of genotype, let's say defined over complex numbers. Okay, and the first fundamental numerical inequality about S is this one. So it's very similar to the Newton inequality, but I think the inequality is better than the previous one. And I find this inequality in Bomberry's paper in, I think, 1973. It's IGES paper, but I don't know if people before that have known this inequality. Maybe I think some Italian mathematicians may have known this, but I'm not sure. So recall that if we don't have this irregularity assumption, so the previous one is like volume S is at least 2 times the Euler characteristic minus 6. So this irregular version is better because they have no constant term. Okay, and the next question is about understanding the extremal case. And it is again Horikawa who did this piece of work. And I think he classified the irregular surface with this volume equal twice of the Euler characteristic. And I think here I want to list some of the classification results. And first, he proved that if the equality holds, then the irregularity must be 1. So it's a smallest possible case. And from this, you can deduce that the Albanese variety of S is just a genus 1 curve. So it's a abelian variety of dimension 1. And then from this observation, you can consider this Albanese fibration. So this A means the Albanese fibration. And here I just write down this Albanese variety of S is just an genus 1 curve. So you have a surface fiber over a genus 1 curve. Then it's natural to study the fiber. And Horikawa proved that this fibration is just a genus 2 fibration. Okay, so this means that this surface S is a double cover over a ruled surface over this elliptic curve, over this genus 1 curve. And then you can use the very classical double cover formula to get explicit structure of S. And this is what Horikawa did. So from this double cover structure, he classified the explicit structure of S. And the third one I want to mention is that he also computed the topological fundamental group of S. And he proved that this topological fundamental group is isomorphic to Z plus Z. So this is the same as the fundamental, this is isomorphic to the fundamental group of this genus 1 curve. And this is also very interesting. So he gave some structural theorem and also some topological description. So, and then if you put some more constraint on S, for example, if you assume this S is of maximal Albanese dimension, which means that the Albanese image of S has dimension 2, then you can have a better inequality. And this inequality is called Sverre inequality. And it was proved by Pardini in 2005, I guess. And this inequality tells us that if your S is of maximal Albanese dimension, then the volume is at least 4 times the Euler characteristic. So this is better than the result of von Behring. And of course, because you have more constraint on S. And then the following question is somehow to describe the extremal case. And this work also has been done by, I think, 2 groups of people. And the first group is Baha, Pardini, Stopino. And the other group is Lu and Kang Zuo. And somehow they classify the extremal case. And in this case, this S is quite simple. The S, if you consider the minimal model of S or the canonical model of S, it's just a double cover over an abelian surface. And the branch locus can be explicitly determined. So that's also very beautiful work. Okay, so this is what we know about geography of irregular surfaces. And the next question is, okay, so you have know a lot about surfaces. How about higher dimensional varieties, irregular varieties? And here I want to introduce, say something about what we know about higher dimensional varieties. So in fact, we don't know much about this. And so first, let me assume this X on this page X is an smooth projective and irregular variety of genotype defined over complex numbers. And under this assumption, the previous severity inequality, we do have a generalization. And this was done by Baha and myself and independently. So we prove that if this variety X is of maximal Albanese dimension, then we have this kind of inequalities. So the canonical volume is at least 2 times the dimension factorial and times the Euler characteristic of the dualizing sheaf. And this is again optimal. So it's a sharp inequality. And we know some examples such that this inequality become equal. And you can just consider some double cover over an abelian variety and branch along a smooth, very ample divisor. So and then you can calculate this example. And but in this higher dimensional case, to fully understand the extremal case is not so easy. And so far, I think there's no complete answer to this question. So, but there are some partial results. For example, I think also Baha, Pardini, Stopino, and recently Zhang, they consider the problem how to classify this extremal case. And I think maybe if the Euler characteristic is 1, then we know something about the extremal case. Otherwise, we only know that its Albanese map is a degree 2 cover. And we don't know where it is branched or where it is unramified. We don't know that. So I think there are many things can be done in the future. Okay, and then today I want to present the theorem is somehow a 3-dimensional version. A 3-dimensional version of the work of Bombieri and Horikawa. So somehow explicitly, I want to generalize those two results in 3 dimensions. Okay, so roughly speaking, I want to prove an inequality and I want to classify the extremal case. So that's the main goal of this talk. Okay, so I think now I can introduce my result. So there are 2 results. The first one is about the inequality, and then the second result is about the extremal case. Okay, so this is the first theorem I want to mention. So this is a joint work with Yonghu, and we suppose that I have a variety X. It is a smooth and irregular threefold of genotype defined over the complex numbers. And the correct version of the inequality is this one. So it's a canonical volume is 4/3 times the Euler characteristic of the dualizing sheaf. So that's the main inequality I want to introduce. So we call this inequality Noether severity inequality, because if you look at this coefficient, it's just the same as the Noether inequality proved by Yongkai Chen, Men Chen, and Chen Jiang. And if you look at the form of this inequality, it is about the ratio of canonical volume and the Euler characteristic. So that kind of inequality is often called severity inequality or severity type inequality. And I think some people also call it Clifford severity inequality. So, but anyway, so severity appears everywhere. So I use severity. Okay, so this is the Noether severity inequality. Okay, And then I want to mention that this inequality is also optimal. So we do have examples showing that the equality can happen. And in this theorem, I also, give some description of the equality case. So suppose you have an irregular threefold of genotype satisfy the equality, then this threefold cannot be so arbitrary. So first, if we consider its minimal model, so note that here, I just assume X is smooth and irregular. I don't assume X is minimal. So by the work of Birka, Kashini, Haken, McKernan, so we can have a minimal model for this X because it's of genotype. And the first description is that if you consider the minimal model, and it cannot have very bad singularities. For example, the minimal model, we proved that it's always Gorenstein. So which means that if X is minimal, then the canonical divisor has to be Cartier. So this is the first property. And the second property is that the irregularity is also 1, which is the smallest possible case. And we also compute the second cohomology of the structure sheaf, and we prove that this is 0. And this quantity somehow is just the geometric genus if the variety is of dimension 2. But if the dimension is 3, so usually it's not so easy to get some information of the second cohomology. And the third property is that if we consider the Albanese fibration of X, note that this Albanese variety of X is again a genus 1 curve. Okay, so you have a threefold fibered over a genus 1 curve. So the fiber must be a surface of genotype. And here we know something about what will be the fiber. So it's a 1-2 surface. So what is a 1-2 surface? It means that this surface is of genotype and its geometric genus is 2 and its canonical volume is 1. So we just call it a 1-2 surface. Okay, and the fourth part is about the topological fundamental group. And we prove that this fundamental group, topological fundamental group, is isomorphic to the topological fundamental group of E. So it's again, it's a Z, 2 copies of Z. It's a direct sum. Okay, so that's the theorem A. And any question about the statement of the theorem? Okay, good. So before I introduce the second one, I want to make some remark first. So that's a remark page. Okay, so the first remark I want to make is that if you put some strong condition on X, then this inequality has been proved by my collaborator. For example, if you assume a priori that X has an Gorenstein minimum model, then the Noether-Severi inequality has been proved by Hu, and I think it's several years ago. So this was known. But usually, we know that in general, we cannot control the singularity on the minimum model of X. So if the minimum model has worse singularities, and his approach may not be applied in the general setting. Okay, that's the first remark I want to make. And the second remark I want to make is that I want to compare the surface case. This is a surface case. And this is a threefold case. So there are some similarities and there are some differences. Okay, so the similarities are like the irregularity. So we know that in the extremal case, the irregularity must be the smallest possible. And this number, this H2, in this case, is also the smallest possible. So we can see that there are some similarities. And in the extremal case for the surface, then if we consider its Albanese fiber, then it's a genus 2 curve. And for threefold, the Albanese fiber is a 1-2 surface. That this is what we have explained. And another similarity is about the fundamental group, topological fundamental group. You can compare this one, and they are the same, almost the same. And the fourth one is a very interesting one, and which is, for me, I think, and my collaborators, at first we do not expect this thing can happen. So for example, if you consider the examples of the extremal case in the surface case, and there's no restriction on this chi. This means that for any given integer, positive integer, we can construct some extremal surface such that this Euler characteristic of this surface equals the integer you have given. But if you consider the threefold extremal case, this is different. For example, if the Noether-Severi equality holds for an irregular surface of general type, then this Euler characteristic must be divisible by 3. So I write here. So this is really something new. The reason is very simple, because the canonical divisor of the minimum model is Cartesian, which means that this number must be even. So you have an even integer, and on the right-hand side, you can get this must be an even integer. So 3 divides the Euler characteristic. So this is something interesting, to us. And we try a long time to understand this phenomenon. And
sorry to interrupt you. Is the volume is just the k cube divided by 3, or you don't divide by 3 the volume?
So here the volume is.
Can you write down the volume? Take a minimum model.
So the definition of the volume. Okay, sorry.
You take a minimum model, right? Okay.
Yeah. So if x is minimal, then this volume of x is just the cube of the canonical divisor.
You don't divide by 3 factorial.
No. That factor has been divided in the definition.
Oh, okay. Anyway, I just confused. Okay. Sure.
Yeah.
Okay, thanks.
Yeah, thank you for your question. So in fact, since the minimum model has a Cartesian canonical divisor, so from the Riemann-Roch formula, you can get this number must be even. So that's something interesting. Okay, so these are some remarks about the first theorem, and I think, okay, so I still have enough time, so I want to introduce our second theorem. But before I introduce the second theorem, I want to spend a page on some basic properties of 1-2 surface. Okay, so I want to study some explicit geometry of 1-2 surface. So suppose I have a surface F. So here I use F because F will be served as a fiber. Okay, so suppose I have a F, which is a minimal 1-2 surface. So recall the definition of 1-2 surface is that the canonical volume is 1 and the geometric genus is 2. Okay, so this surface has a very special property. So since this kf squared is 1 and the geometric genus is 2, then it's easy to see that this linear system, this canonical linear system, has a unique base point. This is the base point is the reason why this kf squared is 1. So if you choose two effective canonical divisor, then they will meet at one point. That point is the base point of the canonical divisor. Okay, so this is about a geometry of one fiber. But now you have a family of 1-2 surface. So you can move the whole move in the whole family, and you will get something interesting. So suppose we have an like X, which is a minimal irregular threefold of genotype, satisfy this condition. So it's just satisfy the Noether-Severi equality. Okay, then by adjunction, you can see that every Albanese fiber is a minimal surface, and it is a 1-2 surface. So on each fiber, you will have a base point. So if you move this base point along this vibration, then here I draw a picture, and you can see you will get a natural section. So this is a threefold fibered over a curve, and using the special geometry of the fiber, we get a section of this vibration. Okay, so I call this section gamma. And this section helps us a lot when we do the classification problem. Okay, so if you keep remember this section. Okay, and then using this section, I can introduce the classification result. So I can give you what will be the explicit structure of the extremal threefold. Okay, so that's the second theorem of us. So it's a theorem B. Okay, so suppose we have an X, a smooth irregular threefold of genotype satisfy this equality. Okay, now I want to understand the structure of such threefold. So to understand it, I can somehow choose a special model to understand. And this model I choose is the so-called canonical model of X. So let this X naught to be the canonical model of X. Then we know that this canonical model is also irregular, and then it is also fibered over a genus 1 curve by our theorem A. Okay, and now I want to make a birational modification of this X naught. So I took some, I took resolution or blow up. So this X naught prime will be a blow up of this X naught. And the center of the blow up is just the section I introduced here. So this is just this section. Okay, and of course you have to make sure that this section, because previously this gamma lies on the minimum mode. You must have proved that this section descends to the canonical mode, and in fact this is not hard to prove. So I just use the same letter gamma to denote the section. Okay, and then suppose I made this birational modification. Then I consider this A naught prime. This one. This is the Albanese map of X naught prime. So this is this map. This is A naught prime. And the theorem tells us that this whole Albanese map can be decomposed into 3 morphisms. So the first is this one. It's a surface S to this Albanese image, which is a genus 1 curve. So what is S? And this S is a P1 bundle over B. And what is this P1 bundle? We know that once you have a P1 bundle over a curve, it's somehow one-to-one corresponds to a rank 2 vector bundle over this curve. And what is the rank 2 vector bundle? And this bundle is just the push forward of the dualizing sheaf. And you can see this is of rank 2 because the fiber is a 1-2 surface. 1-2 surface means that the geometric genus is 2. So this is a rank 2 vector bundle. Okay, and then you have further factorization. So we have a Y. This Y is also a P1 bundle over S. So this Y is a threefold. It's a P1 bundle over a surface. And what is the corresponding rank 2 vector bundle? This is also the push forward of the dualizing sheaf. And this dualizing sheaf is pushed forward by this vibration. So F means the vibration from X naught prime to S. So it's a vibration from a threefold to a surface. And in fact, this vibration is a genus 2 vibration. And you can prove that this is also rank 2. And in fact, it is locally free, and this is not so easy to prove. Okay, and finally, so this is a P1 bundle. This is a P1 bundle. And finally, this one, we can prove that this is a double cover. So X naught to Y, sorry, X naught prime to Y is a double cover. And we, in fact, calculate the branch locus and where this double cover is ramified. So we do have a explicit branch locus, but the formula is too long to write down here. So I just ignore that part. And if you are interested in this part, you can read the paper. But I just want to avoid some notations. Okay, and of course this is too long to understand. So in order for the audience to understand easily, maybe I draw a diagram. Okay, here. So it's a quick understanding of what theorem B said. Okay, suppose I have a canonical model of a threefold, and which satisfies this equality. So the structure of the threefold is here. So this is the original threefold I want to consider. So I choose a blow up along the section, and then I have this A naught. And then the theorem tells us that, so you can construct a P1 bundle over B to get S, and then you can construct another P1 bundle X over S to get Y. And then finally, you can choose a double, you can use a double cover to get this X naught prime. So one can use like one sentence to describe the structure of X naught. So X naught is roughly a divisorial contraction of a double cover over a P1 bundle over a P1 bundle over an genus 1 curve. So it's a 2 tower of P1 bundle. And here, every data, for example, the rank 2 vector bundle and this cover, the branch locus of the cover, all the things can be explicitly calculated. So far, so we have a pretty good understanding of this extremal case. Okay, so that's two theorems I want to introduce. So any question so far? Okay, good. So I still have like 5 minutes, so I want to sketch how we prove this. So here is a sketch of the proof. So the proof is quite involved. So I write down just several steps, and I want to explain in which step what we have proved. So the first step is to make some like simplification or reduction. So in fact, we have proved that if you if you have an irregular threefold, suppose the Albanese fiber is not a 1-2 surface, then we can get a stronger inequality. So that's a previous work of Hu Yong and myself, and we proved that if the Albanese fiber is not a 1-2 surface, then the volume of X is at least twice of the Euler characteristic. Okay, so to prove the inequality, we only need to consider this case. So the Albanese fiber is a 1-2 surface. So here I want to remark something interesting, because for me, we prove this inequality using some method of positive characteristic. In fact, we first proved the characteristic P version of this inequality, and then we use reduction mod P to get this inequality. So far, we don't know how to directly prove this one using like just a complex method. So far, I'm not sure how can we achieve that. But anyway, so that's what we did in the step 1. And in step 2, I think this is the longest part of the paper, and we prove this inequality. So suppose that the Albanese fiber is a 1-2 surface. Then we prove that the volume of X is at least 4/3 times the Euler characteristic, and this is the part we want. And we also get an extra term. So this is the bonus part. So we have an extra term. Okay, and this was done by explicitly study the relative canonical map or relative bicanonical map of the Albanese fibration. So that's so the calculation is very long, but anyway, we achieved that, and this in fact tells us more things. First, it implies the inequality we want, because this is in fact stronger than that one. And this also tells us that when the equality holds, this QX, suppose the equality holds, then this QX must be 1. Okay, so we have the first piece of information about the equality case. And the second one, the third step, we want to get the information about this H2. And what we proved is that if this H2 is not 0, then we will get a stronger inequality. So if this is true, this will imply that Kx cubed is, the volume of X is strictly bigger than this 4/3 times the Euler characteristic. So it's a contradiction. Therefore, this H2 must be 0. And then we also want to study the minimum model. So we want to prove that the minimum model has a Gorenstein singularities. And for this part, we in fact prove this equality. So we compute the H2 of the twice of the canonical divisor. And we prove that this global section of 2K is the same as half of the canonical volume plus 3 times the Euler characteristic. And this will imply that the minimum model has Cartier, has Gorenstein singularity. And this was proved using the Riemann-Roch formula of Miles rate. Okay, so and finally, we want to understand the fundamental group, and this part we use some idea from the work of Gang Xiao, and the reason is somehow like that. So we have a vibration, and this vibration has a section. That's very important. You have a section. You have a vibration with a section, and this means that you don't have multiple fibers. And you know that if you have a 1-2 surface, then the fundamental group is trivial because 1-2 surface over complex numbers are all simply connected. So you have a fibration with general fiber simply connected, and you also have a section. Therefore, the fundamental group of the whole threefold will be isomorphic to the fundamental group of the base curve, so which is the genus 1 curve. So that's also this argument. I saw this argument from the work of Gang Xiao, and I think maybe in the earlier work of like Moschisen, and I think he also used this kind of argument. So this is somehow the proof of theorem A, and I don't have enough time for the proof of the second theorem. So I think it's better to stop here, and I'm happy to answer some questions. Okay, so thank you very much for this attempt.
Thank you. Yeah. Any question from the audience?
Okay, so now I can show up.
Any question? Could you show the last theorem again, theorem B, or the previous page? Yeah, just move a bit up. Okay. Okay, here? Somewhere here. Yeah, the proof of sketch. Yeah.
Proof of sketch. Okay, here.
Yeah, you can stop somewhere here. Okay. So first, if X is irregular, is it clear that chi of omega is always non-negative?
No. There are some results. For example, I think if you have a irregular threefold of general type, suppose its Albanese dimension is maximal.
That's okay. Yeah,
that is always non-negative, but it's possible to have 0 Euler characteristic. But other than this case, I think there are some examples with negative Euler characteristic of the dualizing sheaf. This do happen. But if you assume that the minimal model is always Gorenstein, then this Euler characteristic is positive.
I'm guessing because you look at step 2, if chi of omega is negative, then maybe it's always true, right?
Yeah. Because if the chi is negative, then I think the inequality will be trivial.
Okay.
Yeah.
Yeah. Okay. The other question is a remark about your step 5. So step 5, you mentioned a result of top shotgun, right? Actually, it's let me type a chat. It's a lemma in 1.5 in Norrie's famous paper.
Yeah, maybe.
Okay, so I just typed. So yeah, you are right. So if I have a section, actually, if all the fibers have reduced apart, then you don't need to have section. If all the fibers have reduced apart, then it works. Anyway,
I'm not sure because I think the section is needed, right?
If section, then it's sufficient. Yes.
Yeah. If there's no section, maybe it's just maybe it's finite extension of the fundamental group of the base, I think.
Maybe worse if we have 3 multiple 5, maybe more. Anyway, you look at the lemma 1.5 in Norrie's paper. It's a paper about Sariski conjecture about the plane curve. So.
Okay. Yeah. Thank you very much for this reference. Yes, I only read the paper of Xiao, maybe.
I believe he also referred to Norrie a bit. Yeah. Okay. Anyway.
Okay.
Yeah. Any other question for the audience? Yeah. If not, let's thank the speaker again for the very clear talk. Thank you.
Okay, thank you very much for the invitation. Yeah.
So we have a break until 15 past 4 o'clock local time here. So we still have 11 minutes break. Okay, so then we'll start again. Okay.
Okay. See you later.
Yeah, see you. Yeah. If proof is there, you can upload your PDF, your